Hi, in this video I am discussing about the problems related to manometer. Before starting the problem, let's discuss some basic formulas that is required for solving the problem. Whether the fluid is stored in a storage tank or the fluid is flowing across a pipe, we are interested in finding the pressure on the storage tank or the pressure drop across the pipe. We know that there are two ways we can find the pressure. One is by using mechanical gauges where the fluid is balanced by the mechanical forces, whereas in manometer the fluid is balanced by the manometric high density fluid. The detailed lectures on the concepts on these manometers and mechanical gauges are discussed in separate video. In this video, we will specifically solve the problem. When coming to manometer, there are two types of manometer primarily. One is Utube manometer and another is inclined manometer. So we wanted to find a pressure drop across a pipe from point 1 to point 2. In that case, we will connect one of the limb of the manometer to the point 1 and another limb to the other point where we want to find the pressure drop across this flow line. Few of the general manometric fluids are mercury, carbon tetrachloride. In some cases where the pressure drop is very minimal, the movement of the manometric liquid also will be minimal. In that case, there will be a lot of error. So to have a longer movement so that we can find the pressure head accurately, we can go for inclined manometer. So inclined manometer can be used to find even a smaller pressure drop because due to the inclined limb, the movement of the manometric fluid will be little longer. So we can easily find the height without any error. Coming to Utube manometer, let's discuss what are the parameters that are involved in a problem. One is the density of the manometric fluid, which is mentioned by rho m. Then the density of the working fluid, which is mentioned by rho f. So rho m is for manometric fluid, rho f is for density of the working fluid. Working fluid means the fluid flowing across the pipe. Before allowing the fluid to flow, the height of the manometric fluid in both the limbs of the manometer will be equal. When the flow is allowed to flow, the liquid which is entering the first point will have more energy. Hence, it will push the liquid in the left limb of the manometer, and so the manometric fluid will move through this way, which is counter pressed by the liquid which is coming through this line and the point 2, and it will give another pressure. However, the pressure at this point will be higher because the liquid is entering, so the energy at this point is high. So it's pushing more. After traveling this distance, there will be energy loss because of the friction. Hence, the flowing liquid will not be able to press the liquid more relative to this particular limb. Hence, the left limb will have lower height of manometric fluid, whereas the right limb will have higher manometric fluid level. This deflection in the height of the manometric fluid will help us to find the pressure drop across these 2 points. The height difference between the left and right limb, we can call it as H. That can be used in the formula. So the formula for the Utube manometer is GH, rho manometric fluid minus rho working fluid. G is the gravitational constant, which is 9.81 meter per second square. H is the height difference in the manometer limb. Then rho mf, it's a manometric fluid density. Then rho wf, it is working fluid density. Coming to inclined manometer, as I already told you, when the system's pressure drop is very minimal, we will go for inclined manometer because the moment of manometric limb will be little more relatively to Utube manometer. Again, here also there is a rho f, which is working fluid density, and a rho m, which is manometric fluid density, inclination angle of the manometer limb, which is theta, and the height difference we're going to call it as h. The formula to find the pressure drop across the inclined manometer is delta P is equal to GH sin theta, and again the density difference of the manometric fluid and working fluid. The concepts related to inclined manometer will be discussed in a separate video. As of now, let's discuss the formula here. There are only two manometers that are going to be discussed in your syllabus. One is Utube manometer and inclined manometer. If you closely look at the formula, both the formula looks same, only the sin theta will be excess in terms of inclined manometer. So delta P is equal to GH density difference, delta P is equal to GH sin theta into density difference. So you can easily remember this formula. To understand the concept better, let's start solving the problem. To solve the problem, the first step in solving a manometer problem is to identify what type of manometer is used in the particular question. So once you identify the particular manometer type from the question, we have to write down the formula that is suitable for the corresponding manometer. In this case, if it is Utube manometer, GH density difference. If it is inclined manometer, GH sin theta into density difference. The second stage is to find the height difference between the manometric fluid limb, that is H, followed by the density of the working fluid. So these three steps is the primary for any manometric problem. Coming to the density of the working fluid, the questions will be little twisted. There are 2-3 ways by which density will be given in the question. From that, you have to find the right density of the working fluid. The first way, the given data can be in terms of specific gravity. Specific gravity is a ratio of density of the working fluid by the density of the standard. So on rearranging this equation, I can find the density of the working fluid. So density of the working fluid is equal to a specific gravity into density of water. So coming to the density of the standard, if the working fluid is liquid, the water density can be used as standard density. If the working fluid is gas, then the air density can be used as the standard density. So knowing these density values is mandatory for solving this problem by heart. So water density is 1000 kg per meter cube. In other units, 1000 gram per liter or 1 gram per cc. Cc means ml centimeter cube. So the air density is 1 kg per meter cube. So these two values you can remember. So water is 1000 kg per meter cube, air is 1 kg per meter cube. Whereas the same value can be represented as 1 gram per liter or 0.001 gram per cc. Now the second way by which the density of the working fluid given will be in terms of molecular weight. If the working fluid is gas, usually they will give in terms of molecular weight. We assume the gas should be ideal. Then we know that to calculate the density of ideal gas, the formula is density is equal to pressure into molecular weight by gas constant R into T. Coming to the gas constant, we can use 0.0806 liter atmosphere per mole Kelvin. Since we are dealing with pressure in the equation, it's better to use R value which has pressure, that is the same 0.08206. Coming to temperature, the temperature must be in Kelvin only. The question, they might be given in terms of degree Celsius. You must convert degree Celsius to Kelvin because in the gas constant R, we have Kelvin in the denominator. So to tally the unit, we must substitute the temperature value in terms of Kelvin. Now coming to pressure, the pressure value will be given in terms of any units. So it's better, we should remember these pressure relations. The atmospheric pressure is 1 atmosphere, which is equal to 1 bar, which is approximately equal to 10 power 5 Pascal, equal to 760 mm mercury column. 760 mercury Hg means 760 mercury column. Followed by that, in most cases, the gas cannot be a pure gas, hence there will be a mixture of gases. When there is a mixture of gases, we know that we cannot use normal molecular weight. Since there are many components present in a mixture, we have to use average molecular weight. Average molecular weight can be calculated by finding the ratio of total mass by total moles. So the value in the question will be given in terms of mole percentage or volume percentage or pressure percentage. We know that as we are assuming ideal gas, we can make sure all of them are equal, and from the volume or mole percentage we can find the moles, and then through molecular weight we can convert into total mass and total moles. While solving problem, we'll see that in detail. Let's take the first problem.